hypoventilation. Asthma, for example. Drug overdose. Two common ways to have inadequate ventilation in the respiratory system. Which of the following would be helpful in response to, would be a helpful response in metabolic, that is to say renal, compensation for hypoventilation? So I want to use this one to stimulate a conversation rather than just show you the answer. Somebody, some brave soul, tell me what your answers are and explain.
Well, I said A and C because I said if you increase the carbonic anhydrase.
Increased expression of carbonic anhydrase.
It'll increase the bicarbonate and it'll increase the absorption, which will eventually raise the plasma, and that'll get that renal compensation.
Good.
So that's for A.
Good thinking.
Yeah. And then for C.
Wait, let's just do A first. Let's make sure everybody's reading from your page. Increased expression of, what is increased expression of carbonic anhydrase would increase this process, would make more CO2, and we have more carbonic anhydrase here as well, more CO2, more bicarbonate being reabsorbed. Then, respiratory alkalosis, what are we at? We're in respiratory hypoventilation, which is respiratory acidosis. Respiratory acidosis, we want to increase bicarbonate. And we just explained it. Did I do that right, Mike?
Yeah.
Okay. What was the other one?
And then, so since there's an increase in bicarbonate, obviously there's going to be more of that. And so the increased expression of the NaHCO3 cotransporter is just going to reabsorb more of the bicarbonate faster.
More of this to help the more bicarbonate that we made with carbonic anhydrase to get reabsorbed. So yeah, those were my two answers. Increased expression of carbonic anhydrase and increased expression of the sodium bicarbonate cotransporter. Okay, let's do the next one. It's the same question, just different answers. So anybody want to explain your answers to this one? This one's a little trickier. Sophie?
I said A and C.
A and
C.
D as in David?
C as in cat.
C as in cat. Okay. Yeah, I don't think, let's go through that. Is everybody agree that A is a good answer? Right? Increased expression, same story here. If we increase expression of the chloride bicarbonate exchanger, we're going to increase bicarbonate reabsorption. Increasing bicarbonate reabsorption in the setting of respiratory acidosis would be helpful. Is increasing the expression of the sodium ATPase going to be helpful or harmful to bicarbonate movement here?
I think it would be harmful because it would mess with the gradient for sodium, and that would allow less bicarbonate to go through
Yeah.
the filtering.
So let's go back, let's go all the way back to, I need to go back to the previous PowerPoint. Which I have cleared. So rather than try to dig it out, let me remind you that this box here my screen and this screen are not in sync. Okay. So remember that the sodium bicarbonate cotransporter, sodium is moving up its concentration gradient. sodium is moving from low concentration to high concentration because that gradient was set up by the sodium potassium ATPase. If we increase expression of the sodium potassium ATPase, we're going to make that gradient steeper. And that's going to inhibit sodium bicarbonate co-transport. But if we inhibit the expression of the sodium potassium ATPase, we're going to make that gradient less steep, which will allow more sodium bicarbonate co-transport. That's the idea that you should think of. I don't think this actually happens. I don't think this actually happens in hypoventilation. But it would be helpful if it did. Clear on that? Okay, let's go to Sophie.
So like, how would it increase the expression? Like, is it just like they're making more of,
Yeah, I mean,
like your body's like instantaneously making more of these proteins?
gene expression is regulated, so it takes some time. It might take an hour, but for a gene, so there are sensors in the cells that tell the, there's transcription, that activate transcription factors and increase the expression of the proteins. And sometimes there are these, the proteins have already been expressed. They're in membranes that have not yet been secreted, have not yet been exocytosed into their target membranes. So we can increase expression from the gene, but we can also increase exocytosis of previously manufactured proteins that are sitting here, like in the endoplasmic reticulum, waiting for a signal to get expressed into the surface membrane. Both of those happen.
And how do you decrease?
Decreased expression and endocytosis of surface membrane that takes the protein back in and either waits, stores it and waits for the next time it needs to be put into the membrane, or degrades it. So endocytosis and exocytosis of membrane proteins that you learned about in cell-phys is an important dynamic process for the regulation of expression of these proteins. Thank you. That's a good point to bring back to cell-phys.
And do you have to like hypoventilate or hyperventilate for an extended period of time for like your body to undergo this? Or?
It takes some time.
Okay.
And that's why respiratory alkalosis during altitude sickness can cause some trouble because it takes some time. You feel sick until the body adapts. And that's why some drugs can sort of help the body adapt faster. It does take time. None of these things are happening instantaneously, especially when we talk about expression changes. All right, so let's talk about potassium. Potassium is complicated. So potassium is complicated, and I think the key point that I want you to walk away with is embedded here. That there's the key point. In the key point is that we have mechanisms for potassium excretion. So we can filter it just like sodium, but there's mechanisms for potassium excretion. Why? Because we evolved in a scenario where getting potassium was easy. Grains, seeds, meat, we're omnivores. We evolved in a situation where we were eating all of that stuff. Grasses, not grass, but grains, seeds, meats, fruits, all of those sources are rich in potassium and poor in sodium. And so we ate, well, we still eat a lot of potassium. And so we have mechanisms for reabsorbing it and for secreting it in the collecting tube. Secreting it so that we can excrete it, so that we don't get too much potassium in our body. Why would having too much potassium be dangerous? What would happen if your serum potassium got high? Why would it would be problematic for the heart and for the nervous system? Why?
Like increased levels of potassium that would cause the membrane potential to be even lower.
No, it would be less hyperpolarized. So increased potassium would cause a depolarization of the membrane, of resting membrane potentials. And that would cause the heart to be closer to threshold, and so we might start getting rapid heartbeat. Nerves would be closer to threshold, so we could start getting spasms or, seizures in the nervous system. So we have so potassium has to be kept low in the extracellular fluid. The sodium potassium ATPase helps that, but if we're eating a ton of potassium, we're at risk of getting elevated extracellular potassium, and we want to excrete it. So I think that's the key point. I don't think I'm going to ask you to know the mechanism of that, because it's complicated. But the bottom line is, in the proximal tubule, we reabsorb it. Let's not get into all these squiggly arrows. The proximal tubule is important for reabsorbing potassium, and the collecting tubule is important for secreting potassium when necessary. That's what I mean here. The proximal tubule is important for reabsorbing it, and the collecting tubule is important for secreting it when necessary. This is the one case where we're talking about secretion in the nephron. Secretion into the urinary fluid, so that we can get rid of it, so that it doesn't get too hot. That's what I want you to know about potassium. I will not ask you about these arrows, but I will ask you to know reabsorption in the proximal tubule, and secretion in the collecting tubule, and the balance is determined by the diet. Okay? So let's do another set of clickers. On the last page of this handout, we have 6 clickers, or 6 slides. Let's take another 10-minute clicker break, work on these clickers, and then we'll talk about them together. And then there'll be some time to discuss water. That's where we're going. So let's, take a break, work on these things. You can work together, whatever it takes to sort of re-energize your cognitive abilities, so that we can do another segment of this class related to water reabsorption.